Okay.
This meeting is being recorded.
Super. Well, thank you all for joining. Really excited to have Dirk here to speak with us today.
Here.
Well, here, yes. Truly one of the world experts in relativistic hydrodynamics for many years. Educated in Germany, spent some important formative years in the US, and is back in Frankfurt as full professor for many years, doing really great things. And yeah, thank you so much for taking the time. And without further ado, please take it away. And as you said, just shout if anybody has any questions. We're all friends here. Yeah, we're really looking forward to learning from you today, Dirk. Thank you.
Yeah, thank you, Will, and thanks for the opportunity to do this. I'm also really excited. It's also a special format, not very much in use, that you first give a little introductory thing and then a week later you do the research seminar. But so I did my best to prepare a little bit about the background material that we are going to need for next week's more specialized seminar. So I will start very simple. I'll write down something everybody of you has seen before. I'm sure everybody has, Newton's second law, which I write in the form P dot, which means the time derivative of the momentum is equal to the force. So that's the force. And P, of course, is the momentum. No? Which, since we are all non-relativistic here, we write as mass times velocity. The velocity, of course, is the time derivative, of the position of the particle, r dot, r dt. And how do you solve that usually? Naja, you take the second law and insert the definition of the momentum. No? So P dot is, you assume the mass doesn't change with the time. I mean, in very special cases, this would happen in a non-relativistic setting. If you have a rocket that loses part of its mass by burning fuel, or a car, for instance, but usually your gas tank is not that large compared to the total mass of the car. Okay, and then V dot by definition is R double dot. No? And and this is then F. No? So you solve a ordinary second order differential equation of this form. If the force is given, you know the mass, you just solve this second order differential equation. And the solution is the trajectory of the particle in coordinate space. So if you have coordinate space here, x, y, z, this particle starts out at some position r at time t0, and then it follows the trajectory under the influence of the force, and you have the solution r of t at some later time t. So this is the trajectory in coordinate space. Is my handwriting okay for you? Can you see? Can you read everything?
Looks wonderful to me. Yeah.
Okay, good. For our purposes, we need an alternative to this approach, and without going into too much mathematical details, of course, instead of solving this as a second order differential equation, you could also solve this as a system of first order differential equations. This is also possible. So, for instance, you take the first order differential equation P dot equals F, and you take the first order differential equation R dot equals V equals momentum over mass. Okay, so in principle, you solve this for the two variables, momentum and position, but as a system of first order differential equations. And without the mathematical details, this is a very simple-minded derivation of Hamilton's equations of motion, or the canonical equations of motion. And we call this H1 and H2 for later purpose. Okay, and the solution, this determines a trajectory, but not in coordinate space, but in phase space. Okay. Solution is trajectory in phase space. What is phase space? Well, phase space is a natural extension of coordinate space. The trajectory is now the combination of position space as a function of time and momentum as a function of time. Okay, and of course I can't draw this in this is 6 dimensions. No? I mean, this is still a 3D sort of rendering of coordinate space in 6 dimensions. I'm lost, but let's say if I only have one coordinate and one momentum direction, then you can still visualize this. No? Then you would draw this as let's say x and p, and then this guy starts out here and then kind of moves over here as time goes along. Okay. So that was for for a one-body system. Suppose you now have n particles. Want to treat an n-body system. Then you also have a set of equations of motion, Hamilton's equations of motion, but now you have n times this set of 2, respectively 6 equations of motion. So you have, for each particle which I label with an index I, you have this, and you have this pi over mi, and I runs from 1 to n. And phase space is actually 6n dimensional. Okay. But the whole system is just characterized by a single point in the 6n dimensional phase space. No? So the trajectory is this 6n dimensional vector, let's say R1 of t up to Rn of t, and then P1 of t up to Pn of t. Okay. And it's a single point in the 6n dimensional phase space, but that's of course also hard to visualize. But let's use an alternative, and that's actually something which is good if interactions between particles are weak. So we could draw the individual particle trajectories. So for each particle, so that would be Ri of t and Pi of t. We could draw them in 6-dimensional phase space. No? Each, just like we did it before for one particle, we do it now for n particles. No? And of course, again, I can't visualize this, but in 1 + 1 dimensions, of course, I can still draw this nice little picture here with x here and p here. And then, of course, you have one, before we had one particle that moves like this. Okay, and now I have n particles which move along their individual trajectories. So let's draw a few here, draw a few here, and you can see how this goes. You can interrupt me anytime if something is unclear, or I think it's okay. No? So now, of course, this ensemble of particles is characterized by a distribution of particles in phase space. And this distribution I call F. And it depends on coordinates, momenta, and the time. This is sometimes called the single particle distribution function. And this will be the central object for the remainder of this lecture. How can you put some physics meaning to this distribution? So it's actually related to the average number of particles in a phase space cell. So if you have a phase space cell, oops, phase space cell, and let's put some volume or size to that, and I make it as small as possible. The smallest possible phase space cell has volume h cubed. H is Planck's action quantum. So it's 2 pi h bar cubed. So h is Planck's constant, and sometimes h bar is also called Planck's constant. H bar is h over 2 pi. And if you look at the dimensions of this thing, you'll see that this is precisely the correct dimension of momentum times length cubed. So it's really a little volume in phase space. Okay, and then if I multiply F with an infinitesimal phase space volume d3r d3p and divide this by the volume of this little unit cell or smallest cell, h cubed, then this is nothing but the average in parentheses, because we haven't really defined anything like averaging yet, but that comes in a moment. It's the average number of particles in the phase space volume d3r d3p. And of course, yeah, you see this dependence on R and P, so and on T. So what is meant is actually that this volume d3r d3p is located around R and P in phase space at time t. So if you go to some position RP in phase space at some time t, and you draw a little volume around that, maybe I make a picture. Suppose this is here the R and P vector in phase space, and then you draw a little infinitesimal volume around this of size d3r d3p, then this quantity is just the number of particles, average number of particles located in this little volume. Okay.
I'm sorry, Dirk, may I ask a question?
Yeah, sure.
So far, everything you've done is classical. And certainly on dimensional grounds, I see the point of introducing something that has units of action. But, is there some reason to understand why a quantum unit of action is coming into something that appears classical?
Yeah, there's at this point no reason to do that. I mean, this H could be anything. So and I will also not introduce quantum properties here. I mean, it's natural from the quantum perspective to make this volume not smaller than that, right? Because you can't measure momenta and positions to sufficient accuracy to be so that that you can locate a particle in a volume that is smaller than this. No? Heisenberg's uncertainty relation prevents you from locating anything to better precision than this little phase space volume. But from the classical perspective, you can of course forget about the actual numerical value of H. It's just how I call this, and of course it turns out useful when you do quantum statistics that you choose that phase space cell, not smaller than that. You can choose it larger if you want, but at this point it doesn't matter. Okay.
Thank you.
Sounds good. Okay, good. Yeah, let me make an example so that you have a feeling for what this F is. So F is the actual. It could be completely out of the system. Could be completely out of equilibrium. It's the actual distribution of particles, and how to determine this we will come to later. But you are from statistical mechanics. You are probably used to the concept of local equilibrium. So in local equilibrium, okay, at this point, I don't really make a distinction. Local just means I put little classifiers R and T to some quantities, but in local equilibrium, this distribution function, so the zero means equilibrium, that would go like this Boltzmann distribution. Energy of particles with momentum P. Maybe you have a chemical potential that can depend on space and time divided by temperature. It could also depend on space and time. So for my purposes, this is the single particle energy momentum squared over 2 times mass. For non-interacting particles. Single particle energy for non-interacting particles. Okay. And mu is the chemical potential, and T is the temperature, and they can depend on space and time in local equilibrium. Okay. So now, what can we do with F? I can compute some quantities which are more familiar to you. For instance, let me introduce an averaging, which I usually denote as these angular brackets here. So that's defined as integral over momentum space, not the whole phase space, just momentum space. Okay, I introduced this 2 pi h bar cubed factor into the definition of the integration measure. So this has a dimension. So this integration measure has dimension of density, or 1 over volume, spatial volume. No? And then I have some quantity that I want to put in these angular brackets, and I weigh this with the single particle distribution function. Okay, so this is the definition, and then I can compute some quantities which are familiar to you. For instance, if I average simply the number 1, okay, what is this? I mean, apparently, something happened here. Sorry about this. So if F was the average number of particles in the phase space cell, D3R, D3P, and then I integrate over momentum, then I get, of course, the average density of particles. I said it's the dimensionality of this object is density, or 1 over volume. It's the density of particles which are located at time t at position r. No? This is very clear from dimensions. And then I can generalize this. Instead of 1, I take something else. Let's say chi is an arbitrary function of position, momentum, and time. Okay, and this is some property of the particle. Then, for example, if I take chi to be the single particle energy, which I just introduced in the previous transparency. What do I get then? What do I get? Average of epsilon p is, yeah, you average basically the energy over the distribution. So this object where there's no epsilon p here, and then f as a weight for the averaging. This is, of course, if this was the density, and now I introduce an energy, quantity of dimension energy, and the integral, of course, this is then the energy density, average energy density of the particles at time t and position r. Okay. And now I can also form the energy per particle by dividing energy by density. So in essence, this is epsilon p n averaged over 1 averaged. This is the average energy per particle. Okay. At time t and position r. Okay, let's make another example, which I will make use of later. Let me take the velocity of the particles, p over m, or v, as this chi, and then average v. Yeah, so of course, this would have dimension velocity times density. If I divide by the particle density, I get another quantity with dimension velocity. And that's, as you would expect, it's the average velocity. Let me call this u, r and t. It's the average velocity of particles at t and r. Okay? Is this clear so far? Let me pause for a moment here. I see no objections. No? Daniel, you have a question? You turned on your mic.
I was just going to say it's quite clear.
Okay, very good. Yeah, I hope the level is okay. It's hopefully not too simple. Will said I should start out very, very simple. Okay.
I like it. I like the level a lot.
Okay, very good. Then let's move on. So now, of course, we need to determine this f, okay? How to determine f? So we need an evolution equation for this guy. And what I'm going to show you is a derivation of this evolution equation, which is the Boltzmann equation. Okay, so what will happen? Suppose I have some particles in this phase-space volume d3r, d3p around my position in phase space rp at time t. Okay, and then what happens at some later time? At t prime, t plus dt. Okay, what happens? Of course, all these particles will move around, just like in this picture here, that I've drawn here. So these guys here will move, and then they end up here. All right, but I can, of course, determine where they end up because I know their equations of motion, right? And I just considered an infinitesimal time interval dt. So the new positions at t prime equals t plus dt. The new position will be r prime, which is r plus a infinitesimal position shift. I mean, of course, I assume that you don't get something outrageous in a small infinitesimal time interval. The r is also infinitesimal. Of course, I can multiply dr by 1 dt over dt. So let's do that. dr dt dt. And dr dt is r dot. And if I use Hamilton equation 2, I get r prime is r plus velocity p over m dt. Ne? R dot was velocity. I write it as p over m, but you can also write it as v dot. And the new momenta p prime will also be changed from previous values, and the same or similar calculation using H1, Hamilton equation 1, gives you p plus force dt. All right. Let me call them these equations S1 and S2, like shift, shift in position and shift in momentum. And if nothing happens, right, if these particles don't interact with each other, but just interact due to this force, this external force field, then this is all that happens, okay? And I cannot lose any particle. No? I'm not annihilating or creating, annihilating some or creating new ones. I just follow the particles in phase space, okay? Which means that this number is conserved. The average number of particles is conserved, no? Under this flow. Okay, how can I express this mathematically? The number of particles at new position r prime, new momentum variable p prime, and later time t prime, in a volume d3r prime, d3p prime. Okay, I introduced the normalization factor so that this whole thing is just a number. That is simply what was the number of particles at the previous position, with previous value of momentum, in the previous phase space volume d3r, d3p. Okay, divided by this. So this is a consequence of that. You just transport particles from one phase space point to another. Let me draw a little picture here. Always nice to have pictures in 1+1 dimensions. No? Again, this is how we visualize this. And we had basically some little dx dp here at position x and p. Okay, and then there's the transport. So this was at time t, and then at time t plus dt or t prime, this thing is somehow transported into dx prime, dp prime, and this is the volume. No? dx prime, dp prime is the 1+1, like 2d volume in phase space, and this was here at x prime and p prime. No? So the volume d3r prime, d3p prime, that is in principle different from d3r, d3p, but only in shape, not in magnitude. Okay, you can actually show this calculation. I will not do, but if you are interested, I can show you later or in a discussion. It's a simple calculation of a Jacobi determinant. So you would have to, if you change these variables back to the old variables, you would have to compute a Jacobi determinant of this kind, 6-dimensional Jacobi determinant. Then you perform the variable shift. This is the Jacobi determinant. And if you go to the definition of this object, again, I postpone this to the discussion. You use Hamilton's equations of motion. You show that this guy here actually is 1 plus terms of order dt squared. So to first order in the infinitesimal time, it's 1. Okay, so the volume does not change. The shape may change, but the volume does not change. Okay, then you use this result in our equation up there. Here, you use this result in this equation. And you divide out the factors which are common on the left and the right hand side. And you obtain a very important result. That the transported distribution, sorry, forgot the prime at the t. So that mistake also here. Is actually, oops, sorry, is actually the old one. If you just transport, it's just nothing that happens. But now I can, of course, from the previous transparency, no, sorry, from the same transparency up here, S1, S2, they tell me exactly how R prime and R and P prime P are related. So on the left-hand side, I insert this relationship. R plus, okay, P over M dt. I could have written velocity. Naja, let's stick to my script. And T prime is of course T plus dt. And that's equal to the old one. Okay. And now, of course, you immediately suspect what will happen. Now, I will Taylor expand the left-hand side because the arguments are shifted by infinitesimals. So I can do Taylor expansion up to first order in infinitesimals on the left-hand side. So if I expand around R, P, and T, then the expansion point gives me f of R, P, and T. And then I get the first non-trivial term in the Taylor expansion. And I have to do this in all variables. No? So let me sum over the components x, y, and z of coordinates and momenta. And then I have to take the first partial derivative of f with respect to the ith coordinate. And then, of course, the differential in coordinates, which in this notation where I take every component of vector separately and label them with an index I. So the differential is this P over M dt. This is the difference between R prime and R, the expansion point. So it's the ith component of momentum over M times dt. All right, and then I do this for all spatial coordinates, for all components of the spatial vector R. Then I do the same for the momenta. So I take the partial derivative of f with respect to momentum pi, and then the differential, which is fi dt. And then there's one more term in the Taylor expansion, one more variable which I have to consider in the expansion, which is the time. So it's df dt. That's the Taylor expansion of the left-hand side up to first order in dt, the infinitesimal time. And the right-hand side, of course, stays as it is. All right. And that's basically it so far. I think, is this clear so far? You following me? Taylor expansion of functions of more than one variable.
Yeah.
Oh, good. Okay. So now I cancel the same term on the left and the right. And then I write what I had here in the following way. So it's 0 equals df dt. Okay, and then I put the vectors back together. No? So you have momentum over mass times the derivative of f with respect to the components of position vector. This is the gradient in position space. If I take this as a scalar product of two vectors, this would be p over m scalar product with nabla r with respect to spatial coordinate. Okay, I think you're familiar with this. No? Nabla r is this d by dx, d by dy, d by dz. Okay, And the scalar product of two vectors, I think, is also clear. No? It's basically what I had down here. Okay, and then the same for the last one. So it's F vector dot. Okay, and then I have to introduce this gradient in momentum. So this is basically nothing but d by dpx, d by dpy, d by dpz. Okay, and this is the equation I was looking for. This is the Boltzmann equation in the absence of collisions. Actually, with the fourth term, it's sometimes also called Boltzmann-Vlasov equation in the absence of collisions. All right, and that partial differential equation gives you f, the distribution function, which you were after. All right. So far, so good. I hope. No complaints. Good. So now, of course, what do we do with collisions? I mean, collisions are important. So far, we have neglected them. So what do? I make a couple of assumptions to simplify the treatment. So the first assumption, A1, is system is dilute. That means you only consider binary elastic collisions. Okay, the elastic part is not necessarily a consequence of the diluteness, but dilute means also somehow low energies, no? So you won't do inelastic collisions, creating new particles or whatever. So consider only binary elastic collisions. And let me draw this collision process. So I actually have a particle with momentum p that collides with another particle, let's say, that has momentum p1. Something happens here, which you can compute from quantum mechanics, if you like, if you really want to do this as a quantum problem. But at the end of the day, these two particles will emerge again with different momenta, p prime and p1 prime. And let me call W p1 goes to p prime, p1 prime. Let me call this the transition probability for this collision process. So I don't want to introduce cross sections at this point. You can do this, and you can look this up in the literature if you like. But I can dispense with this in the simple treatment. Okay, you have to assume that the range of interaction, so that means basically the range where this collision process happens, R int, is much, much smaller than a quantity which we call the mean free path. So that means between collisions, the particles propagate it in a non-interacting free manner. And then that distance which they propagate is very, very large. And then there's something happens in a small range of interaction, and then again they propagate free. This allows you to neglect correlations between the particles, between collisions, okay? You treat them as free between collisions. This is sometimes also called the molecular chaos assumption. If you look this up in the literature, you'll find this. Another important assumption is that over the range of the interaction, F can be considered as constant. So the collision process is localized. So in mathematical terms means that that gradients in space of F or variations in time of F are much, much smaller than F divided by R int. Okay, so the change of the distribution function over the range R int in space and time is much, much smaller than F itself. And I multiplied factors of light velocity, 1 over light velocity in here to give everything the same dimension. And that's also why I need this velocity factor in front of the spatial gradient. Okay, so F constant over this range R int. And then the final assumption is also considers this gradients in momentum. Okay, so also here, gradients in momentum with the proper dimension are much smaller than F over R int. And this means that you can neglect the effect of the force in the range where collisions happen. Effect of F on collision process is negligible. In principle, this is an assumption that the forces acting on the particles which curve the trajectories between collisions, they are not that strong. Okay, this is what this last thing means. Okay, so now what happens to the Boltzmann equation if you include collisions? Let me abbreviate the right-hand side here in the following by this capital DF. So this D is an operator, which means I take all these derivatives on the left-hand side, acting them on F. Okay, just for notational convenience. So if I introduce collisions, then the Boltzmann equation will change. And there will be something on the right-hand side, which I call C, which is the collision term. And the collision term has two parts. The collision term has a gain part, which I call C plus, and the loss part with a proper minus sign, minus C minus. Okay, so that's the gain, and that's the loss. What do I mean with gain and loss? I mean, if you look at this collision process here, if you look at this collision process, you see you started with some particle with momentum p, but it interacted with some other particle, collided with some other particle, and at the end, the momentum of that particle has changed. It's p prime. So that's a loss part. No? It's a loss for the range of momenta around p. No? The range of momenta around p, the particles in that range get depleted because they collide and then are moved into a different momentum volume element around p prime. All right. Did I say this in an understandable way? Let's see. Get some feedback from you.
Could you repeat it? I was just still too focused on writing. Just
okay. You don't need to write this. We can put this. I can send you that or. Okay, but anyway, yeah, good. Let me repeat it anyway. It doesn't matter. So you started with some particles in the momentum range around p, and they collide, and then they end up somewhere else in momentum space. They end up with momenta p prime. So after the collision, such a particle is moved away. So you get a depletion in the momentum range p since due to collisions. So this would be a typical part of the loss term. You would lose particles due to this particular collision process. The particle no longer has momentum p. After the collision, it has momentum p prime, or maybe p1 prime if you cannot distinguish these particles. But they don't have momentum p. It's a different momentum. So it's a depletion of particles in that little phase space volume element, which is located at R and P. Okay.
Yes, understood.
Thanks. Yeah, very good. So this is the loss. All right. So this was the typical thing here. So you have P1, P, collision. At the end of the day, new momenta P1 prime, P prime, but no longer P. But on the other hand, you can also imagine that there are collision processes where you start out with the reverse, P prime, P1 prime, and end up with P1 and P. So you also, you also gain particles in the momentum range P, in the momentum range around P, so the range D3P around P, by collision processes. So some particles scatter into this range. Okay, so you lose some particles, you gain some particles, and this is somehow balanced by the difference C plus and C minus. Okay, if you scatter more into the range, C plus will win over C minus. If you scatter more out of the range, C minus will win over C plus. Okay, and then you can write down these terms. And for that, I just do some hand-waving arguments, but of course, these terms must be proportional to the transition probability for this process. No? So P prime, P1, sorry, this was writing the loss term. Writing the loss term, so that's the second part. It must be proportional to the density of collision partners. Okay, what is the density? This was n. No? The collision partners have momentum P1. So I write the density as the integral over d3P1 over 2 pi h bar cubed times f of r. Everything happens at r. It's localized. And t. So this is basically n1 of r and t, the density of particles of collision partners. And then, of course, if there are more particles with momenta r, p, and t, then of course you will also get more loss. No? So the more you have, the more you can lose, because the more of these collision processes will happen. So this is basically what C minus is proportional to. And then, of course, you don't observe the final state momenta. So at the end of the day, you would also integrate over the final state momenta, which are unobservable. Okay. And then you already have an expression for the loss term. Okay. Following, I will abbreviate this with F, and this here with F1. And then the gain term you also have to worry about. How does the gain term look like? The gain term is, of course, also proportional to the transition probability, but now you have to be careful. The momenta are reversed here. Okay. And then it's proportional to the density of P prime and P1 prime particles. So, oops, D3 P prime F of R P prime and T, and the density of P1 prime particles, all right, F R P1 prime T. And at the end of the day, you also have to integrate over. Oh, here was a mistake. Sorry. You also have to integrate over the unobserved P1 particles, because the P1 can take any value in this collision process, and this would be C plus. Okay. And actually, there is a principle of microscopic irreversibility. So these two guys are equal to each other. It's the principle of microscopic irreversibility. Basically, microscopically, you can look at the reverse process, and the probability must be the same. If the interactions are given between the particles, quantum interactions between the particles, it doesn't matter. The transition probability should be the same. Okay, and then you can write.
Quick question.
Yeah.
Why is it called an irreversibility and not
reversibility? I'm sorry. Thank you. Great. Yeah. Fantastic. Reversibility. Thank you. Yes. I was just a test to see whether you're still with me. It's already nearing the end of my hour, I guess. Well, I can probably be a little bit flexible with the time, or
Oh, yes, please keep going. This is excellent.
Okay, thanks. I will not keep you from lunch if you haven't had it yet, but I still have a few pages, and I think it may be interesting for next week. Okay, so let's write everything. You see many things are the same here. No? I mean, you always integrate over the momenta of the particles that don't interest you, the partners or the final state guys here. D3P1. Okay. And then this microscopic reversibility principle allows you to, when you take the difference between these two terms, to factor this out. Factor this guy out. And then you basically have a gain, which was F1 prime and F prime. So F prime, F1 prime, minus loss, FF1, minus FF1. Okay, and then you have it. That's the collision term in the Boltzmann equation. And that's about it. Okay, that was a quick and dirty derivation of this, I hope. But I hope it's understandable. Yeah? I mean, it's some physical principles about, densities of collision partners and unobserved final momenta, so you integrate over them. But in essence, this is what it is. Okay, and this collision term has interesting symmetry properties if we are allowed to integrate over the last momentum here, the P. Symmetry properties. Okay, so what I will do is actually I multiply this guy C with this function chi, which I introduced previously, some function which depends on Rp and T. Some particle property is chi, and then let me integrate over all momenta. Okay, so the point now is, of course, now you integrate over everything. You write this out. It's basically D3P, D3P prime, D3P1, D3P1 prime over 2 pi h bar 12. Chi F prime F1 prime minus FF1 W. Okay. Yeah, let me write this out. So, okay, and you see the symmetry properties I'm alluding to are related to exchange of integration variables. So, if I interchange P with P1 and P prime with P1 prime, what will happen? Okay, microscopically, the same as if you look at the reverse process, microscopically, it can also not matter how you label the incoming and outgoing momenta. So in principle, this transition probability also has a symmetry property. I can exchange the momenta in the incoming channel, and I can also exchange the momenta in the outgoing channel, or I can, of course, change them simultaneously. So this is basically the change of pairwise change, incoming change or outgoing change. But of course, it also means that under the simultaneous change of integration variables, okay, this W will always be the same. Okay, and of course nothing happens here in this difference of distribution functions. If I change P prime to P1 prime, this sorry, there was an undo button, but I forgot where it was. Here. In this here, this becomes F1 prime F prime, which is the same, and this becomes F1 F, which is still the same. So nothing changes here in this latter part, nothing changes in the integration measure, but chi, which depended on P, becomes chi dependent on P1 under this exchange. So you get chi 1 under this exchange. Otherwise, of course, you didn't do anything. It's still the same thing, right? So now I have to change, unfortunately, I have to change the pages. So my integrated collision term, I could write this now as okay, let me abbreviate this whole thing here by d capital P, so I don't have to write everything. D capital P integration measure. It becomes chi 1, and then times f prime f1 prime minus f1 times w. But this was the same as writing chi, because of the symmetry. So I can write this as 1/2 chi 1 plus chi, because it's the same. All right. Give you a moment to digest this or to ask me questions. All right. Then I do another interchange. Now I change incoming and outgoing momenta and use the principle of microscopic reversibility. Always discover some mistakes. All right.
Sorry, quick question. On the right hand side, in the top line, what is this E, capital P or capital D?
DP, no? You mean this guy here?
Yes.
Yeah, I abbreviated the integration measure, so I don't have to write this whole thing here.
Okay.
I call this DP. Yeah.
I missed that.
Yeah, thank you. Yes. Otherwise, I'm writing until 2 o'clock, so that's not good.
Yeah.
All right. So if I do this interchange now, you see, now something interesting happens. Under this interchange, this guy, this product here becomes this guy. So what will happen is that under this interchange, of course, the microscopic reversibility doesn't do anything to the W, that is the same. But what happens is that this becomes basically F1, all right? This here. So I could pull this out. No? I mean, I have to be careful though. This becomes this, but it isn't 0 because this here becomes chi 1 prime plus chi prime, no? Under this interchange. Sorry, now this is hard to read. Sorry, let me write this again. So this becomes FF1 under this interchange, and this becomes chi 1 prime plus chi prime. Okay, so I can write the right hand side also as 1/2 dp chi 1 prime plus chi prime times F1 minus chi 1 minus chi times F1 times W. Okay. All right. This was hopefully not too quick, this manipulation, but basically this goes into this goes into this. But for the second term, I don't do anything. I don't do this interchange. Otherwise, of course, everything would become the same again. This I leave as it is. So with this minus and the FF1 pulled out, I still have this minus chi 1 minus chi. So this times this previous term. Is this more or less clear? Hopefully I didn't lose you now. So for the first term, I do this interchange. The second term I just leave as it is. First term under this interchange becomes this times ff1. The second term I just leave with the minus sign. It's minus chi1 minus chi times ff1. So it was just to pull out the ff1. Okay, I hope it's more or less clear. So this here I will call delta chi for some reasons which will become apparent right now. So in collision processes, there is something which is called a collisional invariant. And the collisional invariants are quantities which are conserved in these binary elastic collisions. For example, what is conserved in the binary elastic collision? Particle number, of course. No? Particle number, it's similar as here. No? For particle number, this chi quantity is 1. So let's take chi equal 1. And then, of course, delta chi, for each particle, chi is 1. So chi 1 prime is 1, chi prime is 1, chi 1 is 1, and chi is 1. Yeah, that's 0. Delta chi vanishes. Another example is energy. For energy, we have to take chi equal to the single particle energy, epsilon p. And then delta chi is, read it off in the definition up here. It's epsilon p1 prime plus epsilon p prime minus epsilon p1 minus epsilon p. Yeah, but if these are elastic collisions, energy, single particle energy is conserved. The sum of incoming energies is the same as the one of outgoing. And of course, the last quantity that you certainly have suspected is conserved, is a collision invariant, is the momentum. And in binary elastic collisions, also momenta, sum of outgoing momenta is equal to the sum of incoming momenta. In this case, this is a vectorial quantity. All right. So if I have still 5 minutes, I will present you the conservation laws that follow from this property that you have collision invariance. Is this okay, Will? Five more minutes?
Yes, please.
Okay, good. The conservation laws, and then of course, then you have everything for next week's seminar talk. Which, of course, I also have the relativistic generalization. Maybe I can be brief on that. So for the conservation laws, you have conservation of particle number, and all you have to do is you integrate the Boltzmann equation over momentum, and the weight is 1. And then the left-hand side of the Boltzmann equation is df, and the right-hand side was this integral that we just considered up here, right? This integral here with chi equal 1. But for chi equal 1, we just showed that the right-hand side features a collisional invariant, delta chi equals 0. So the right-hand side vanishes. So this here vanishes if you take chi equal 1. So, but this was the right-hand side of the Boltzmann equation when you integrate over d3p times 1. So the right-hand side is 0. Okay. So I mean, the Boltzmann equation looked like this here. df is this collision term. We just integrated the left-hand side, multiplied with 1, integrated over d3p. That's the left-hand side. The right-hand side is precisely this guy here with chi equal 1. For chi equal 1, delta chi is 0, as we just showed. So the whole right-hand side vanishes. Okay. Now all you have to do is manipulate the left-hand side a bit. Okay, let me be a bit brief on this. Maybe this is also something if you have questions, or maybe you want to do a little homework exercise. So here you basically insert the definition. And then you move derivatives out of the momentum integral. So you can easily move out the time derivative out of the momentum integral. And you can easily move the spatial derivatives out of the momentum integral. For this term, you would have to work a little harder, but you can actually show it will vanish at the end of the day. But if this force doesn't depend on momentum, let me neglect the force for sake of simplicity. Otherwise, the discussion will be too long. So let me put the external force to 0. Let me just focus on the two terms that remain. So I would have d by dt of an integral 1 times f, and I would have spatial gradient acting on an integral where you have, let's look again, velocity times f equals 0. And this quantity we already introduced. This was the particle density. And this we also introduced. If you divide this by particle density, it's average velocity. So if you don't divide this, this is particle density times average velocity. Okay, and this is the continuity equation for particle number, well known from, for instance, electrodynamics. Density times velocity is, of course, the current, particle current. Okay, and if you do the same manipulations for, now I'm really quick, but you can now complete it yourself. You take chi equals to the single particle energy. At the end of the day, the same steps give you d by dt energy density plus spatial gradient of a quantity which I call momentum or energy flux density. We'll define this in a moment for 0. So this guy here is actually the average of energy, single particle energy times velocity, which is what you would call energy flux or momentum density. Momentum or energy flux density. And that's, of course, the energy conservation equation. As is known from hydrodynamics. And then the final thing is, of course, momentum. You can do the same manipulations for momentum. Chi is P. And you get momentum conservation. Okay, these steps you can fill in now because it's the same as we did before. So the first term is actually, yeah, maybe write it out in this form. It's actually P averaged. And then you have a term where the spatial gradient, let me write it in this form, acts on a tensor, which is Pi Pj over M average. And then we neglect the force part for sake of simplicity. So this guy here is actually, if you divide by M and multiply by M, you see this was the velocity density that we introduced previously. So it's M times density times average velocity. So it gives you the time evolution of the particle current, which is actually momentum, if you multiply with mass. In this guy here, I call this a new quantity, which I call capital Pij, RT. This is the shear stress tensor. Including the equilibrium part, so not only the non-equilibrium part. And you get, of course, momentum conservation from this. So the momentum of the system written as mass times density times average velocity plus, okay, now of course I can go back to the scalar product notation if I write the tensor with this double arrow, okay, equals 0. That's momentum conservation. Okay, so these are the conservation laws which actually govern the dynamics of fluids, hydrodynamical conservation laws. Okay, and the only thing I want to briefly mention is the relativistic generalization, and then I'm done. Next week we will do everything relativistically, of course. But it's actually simple. Our velocity in the non-relativistic context was momentum over mass. Relativistically, velocity is momentum over energy. And energy is now not, of course, the non-relativistic energy, but it's the relativistic energy of the particle. And to get the dimensions correct, you need another c² here. Okay, and then my Boltzmann equation is not I can immediately get it if I replace the velocity that I had before, p over m, by this relativistic expression. Let me neglect the fourth term again. It's a little bit more complicated in relativistic language. This was if I just put the p over m velocity as this relativistic velocity, multiply with energy and divide by c². And this relativistic collision term on the right-hand side, I write as this script c, just for sake of brevity. And then I know that my momentum for vector is p mu, is energy in the time component and normal spatial momentum in the normal spatial component. And my foregradient, my relativistic foregradient, del mu is d by dct and the standard spatial gradient. Then you put everything together and you see the first two terms in this Boltzmann equation actually become the scalar product of four momentum with foregradient acting on F. Okay, and that's the relativistic Boltzmann equation. And that's it. That's the equation we will use profusively next week. And okay, the other thing you have to also adjust is this averaging. You have to integrate not over non-relativistic momentum space, but you have to integrate over Lorentz invariant momentum space. That means you need another factor of 1 over energy, relativistic energy, in the averaging process. And then you see that actually the particle forecurrent is the average of the four momentum. I'm not going into the details right now. And p nu is actually the energy momentum tensor, T mu nu. So it's the particle forecurrent. And this is the energy momentum tensor. Momentum tensor. And the conservation laws that we derived previously can be immediately generalized relativistically. I mean, you take basically this Boltzmann equation, you perform this averaging, you use the properties of the collision integral that we have already discussed. I'm not going into the details now, but then you see that particle number conservation is this continuity equation, and energy momentum conservation can be written in this very succinct form, L nu T nu equals 0. Okay, that was all I wanted to tell you today, and I hope it was not too quick in the end. And yeah, but I think there's still time to ask questions if you're interested.
Super. Really, thank you very much, Dirk. I have questions, but let me throw the floor open to others if they have questions first.
Yeah,
I would only ask for the write-up, so I can read it again properly.
Yeah. Despite my sloppy handwriting in the end.
It's better than what I managed to write down. So
yeah. Okay. I can save this notebook here, and then let me see, how do I do this? Ah, okay, yes. How would that work? Okay, let me do this. I'll send it to Will, and he can distribute it. Huh? Is this okay?
Yeah, absolutely. Happy to.
Great, thank you.
Yeah, I will probably have to not move to trash. That would be bad. Okay. Yeah, I think we lost a little bit of the audience at the end, but
yeah, it's a shame. Herbert, did you want to say something or ask something?
Yeah, no, just say handwriting. Don't worry about your handwriting. Way better than ours. This will, and we'll see that we put this up.
okay.
If you get it to us.
Yeah, I'll just send you a PDF of this. I think that's the best.
Perfect. Thank you.
Well, before you wrap things up fully, Dirk, I have one sort of physics question. Well, at least one, but the one that I really want to ask is related to several pages back, sort of the fundamental point that you made that the average particle number is conserved. And
let me see, where was that? Here.
Even further back. I mean, really, I didn't want to break up your flow. I thought it was probably going to be something very simple. Even further back.
You mean here this argument about the
yes, this one. Whoops.
Yeah. I guess it was here.
Right here. Right, exactly. So certainly if the total number of particles is conserved. So I would say if you add an integral to both sides, I would certainly agree. What is the argument that you can get rid of the integral sign?
Yeah, I mean, basically it's the infinitesimal time step. So what you assume is, of course, that in this picture is maybe a little bit misleading. And maybe this distance here is a bit too large, the dt prime. If this is dx, this is dp, then that should be this volume should be close to that one. So it's basically you can only flow the particles, and you cannot. I mean, of course, one may. I mean, this could be deformed. So one particle could move a bit further away from the others, but you still include this in this new volume element, which is deformed with respect to the old one. So I mean, you catch them all in this infinitesimal time step. All that was in here, you catch them in the new on the left hand side in this particular. I mean, it wouldn't work if some guys flow out or some others come in from somewhere else, right? Then it wouldn't work, this argument. But you do this infinitesimally, and you just follow the tracks, following Hamilton's equations of motion, and then you do the sampling again to catch all of them that you started out with. Yeah, in some sense, if you like, this is also an assumption, but yeah, it's. I mean that the mathematically rigorous definition goes, of course, the other way around. So you start with Liouville's equation, which is actually this conservation law. Okay, but it's an equation for the whole n-body system, and I didn't want to go into all the mathematical details.
Super, thank you. That's the word I was looking for. I knew that there was some person.
Yeah, Liouville's equation, but this is in phase space, of course, no? And it's in 6 n-dimensional phase space, no? And then you would have to break it down and neglect correlations and invoke BBGKY hierarchies and stuff like that, which of course I wanted to avoid.
No, mercifully, you kept it from us.
Okay. Yeah, I hope the people didn't drop out too soon. I didn't follow who was still following. I think fairly long time. I saw still a lot of you guys there, but then eventually they dropped out.
Yeah, I think it's super good. And the nice thing that because you have agreed to record this, we will throw it up onto YouTube, and people who had to go because of time can watch what they missed. Okay, sounds good. Super. So let me in fact, on that note, end the recording.
Recording, yes.
Okay.